Have you ever wondered why a small increase in speed can make a moving object much harder to stop? A package moving on a conveyor belt, a skier going downhill, or a car speeding up on a road all have something in common. Their motion is connected to energy. In the previous video, we introduced work as a way of transferring energy using a force acting through a displacement. In this video, we will connect that idea directly to motion. We will learn that when net work is done on an object, its kinetic energy changes. This gives us a powerful shortcut. Instead of always finding acceleration first, we can sometimes solve motion problems by tracking energy. By the end of the video, you should be able to calculate kinetic energy, use the work energy theorem, and recognize when the work energy method gives the same answer as Newton's second law. Kinetic energy is the energy an object has because it's moving. The equation is Ke equals 1 half mv squared. Here Ke is kinetic energy measured in joules. The symbol m is the mass of the object in kilograms and v is the speed of the object in meters per second. There are two important ideas in this equation. First, kinetic energy depends on mass. If two objects have the same speed, the object with the larger mass has more kinetic energy. Second, kinetic energy depends on speed squared. This is very important. If the speed doubles, the kinetic energy does not simply double, it becomes 4 times larger because the speed is squared. This is why faster moving objects can be much harder to stop. A small increase in speed can produce a much larger increase in kinetic energy. Also notice that speed is used in the equation, not velocity. Kinetic energy is a scalar quantity. It does not have direction. An object moving to the right at 5 meters per second and an object moving to the left at 5 meters per second have the same kinetic energy if their masses are the same. A change in kinetic energy is one possible result of doing work on a system. If positive net work is done, the object's kinetic energy increases. If negative net work is done, the object's kinetic energy decreases. Now let us connect work to kinetic energy. Consider an object acted on by a constant net external force. The object moves a distance d in the same direction as the net force. Since the force and displacement point in the same direction, the work done by the net force is simply W equals F net times d. But from Newton's second law, the net force is m times acceleration a. So we can write the net force as ma times d. This may look like a force problem, but it is about to become an energy problem. The key connection comes from kinematics. When acceleration is constant, we can relate initial speed, final speed, acceleration, and displacement using the equation v final squared equals v initial squared plus 2 times acceleration times the displacement d. That means the quantity a times d can be replaced by a speed expression. Once we do that, the work done by the net force becomes connected directly to the change in kinetic energy. This slide shows the mathematical connection between work and kinetic energy. Starting from W equals m times AD, we use the kinematic relationship to replace A and D with 1 half V final square minus V initial square. So the net work becomes 1 half m times V final squared minus 1 half m V initial squared. But 1 half mv squared is kinetic energy. Therefore, the net work done on the system equals the change in kinetic energy. We write this as W equals delta Ke, which equals Ke final minus Ke initial. This is the work energy theorem. In words, the net work done on an object equals the change in that object's kinetic energy. If the net work is positive, the object speeds up. If the net work is negative, the object slows down. If the net work is zero, the kinetic energy does not change, so the speed stays the same. This theorem is useful because it allows us to connect forces and displacement directly to change in speed without always solving for time. Let us apply the kinetic energy equation to a package moving on a conveyor belt. The package has a mass of 30 kilograms and its initial speed is 0.5 meters per second. Part A asks us to calculate the initial kinetic energy of the package. Before calculating, notice that the speed is small, only half a meter per second. So we should expect the kinetic energy to be relatively small, even though the mass is 30 kilograms. The equation we need is kinetic energy equals half mv squared. For part A, we substitute the given mass and speed into the kinetic energy equation. Kinetic energy equals 1 half times 30 kilograms times 0.5 meters per second squared. The speed squared is 0.25 meters squared per second squared, multiplying by 1 half times 30 gives 3.75 joules. So the initial kinetic energy of the package is 3.75 joules. Now the problem becomes more interesting. A constant applied force of 120 newtons pushes the package through a distance of 0.8 meters. At the same time, friction opposes the motion with an average force of 5 newtons. Part B asks for the net work done on the package. Part C asks us to calculate the work done by each force separately and then add them. Part D asks for the final speed using work and energy. Before doing calculations, let us identify the forces. The applied force points in the direction of the displacement, so it does positive work. Friction points opposite the displacement, so it does negative work. The weight and normal force are vertical. Since the package moves horizontally, those forces are perpendicular to the displacement. Therefore, the work done by weight and the normal force is zero. This is an important point. A force can act on object and still do zero work if it is perpendicular to the displacement. For part B, we can first find the net force in the horizontal direction. F net equals F applied minus F friction, and this is equals to the applied force is 120 newtons minus the friction force is 5 newtons. So this is minus because it is in the opposite direction. Therefore, the net force will be 115 newtons. Since the net force and displacement are in the same direction, the net work is F net times D. F net is 115 newtons times D is 0.8 meters, and this is equals to 92 joules. For part C, we calculate the work done by each force separately. The applied force is in the same direction as the displacement. So the angle is 0 degrees, and we can write W applied equals F applied times D cosine 0 degrees, and this is equals to 120 newtons times 0.8 meters, and this gives us 96 joules. And friction is opposite the displacement, so the angle is 180 degrees. We can write W friction is equals to F friction times D cosine 180 degrees, and this is equals to negative force of friction times D, because cosine 180 is negative 1, and we get negative 5 newtons multiplied with 0.8 meters, and this is negative 4 joules. And the work done by the force of gravity is equals to 0, and also work done by the normal force is equals to 0, because force of gravity and the normal force are in the vertical direction, and we do not have any displacement in vertical direction, so the work done by the gravitational force and the normal force will be 0. Now we can write the total work. W total is equals to W applied plus W friction plus W gravity plus W normal force, and here W applied is 96 joules, and then W friction is negative 4 joules, and then the work done by gravity is 0, and the work done by the normal force is 0. So this gives us 92 joules. Same answer we got in part B. Now we use the work energy theorem to find the final speed. The net work is 92 joules. The initial kinetic energy is 3.75 joules. The work energy theorem says that net work equals final kinetic energy minus initial kinetic energy. So the final kinetic energy equals the initial kinetic energy plus the net work. Now we know the kinetic energy is given by half mv squared. So we can use this equation here and rearrange. So we have half mv final square equals initial kinetic energy plus the net work. And we can rearrange this equation. So let's multiply both sides by 2 and divide by m. And we get Vf square equals 2 divided by m times Ke naught plus W net. And from here we get V final equals square root of 2 divided by m times initial kinetic energy plus net work. And we can substitute the values here. So we get V final equals square root 2 divided by 30 kilograms times the initial kinetic energy is 3.75 joules plus the net work is 92 joules. And this is equals to 2.53 meters per second. We can solve the same problem using Newton's second law and kinematic equations. Net force is equals to mass times acceleration in x direction, and we can rearrange this to find the acceleration, which is net force in x direction divided by the mass, and we can calculate this. Net force is 115 newtons divided by the mass 30 kilograms, we get 3.83 meters per second square. And then we can use the kinematic equation. V final square equals V initial square plus 2 times acceleration times the displacement. And here we can rearrange this equation to find V final. So V final is equals to initial velocity squared plus 2 times acceleration times the displacement square root. And we can substitute the values. So the initial velocity was 0.5 meters per second. So this is squared plus 2 times the acceleration 3.83 meters per second square times the displacement 0.8 meters and this whole thing square root. And this gives us 2.53 meters per second, which is the same answer we got using the work energy theorem. The work energy method and Newton's second law method agree because they describe the same physics. The difference is how we organize the problem. Now let us look at an example where work energy becomes especially useful. A 58 kilogram skier is coasting down a 25-degree slope. Near the top of the slope, her speed is 3.6 meters per second. As she moves downhill, the component of gravity along the slope speeds her up. At the same time, kinetic friction with a magnitude of 71 newtons opposes her motion. We are asked to find her speed after she moves 57 meters downhill. Air resistance is ignored. The important idea is that the skier's displacement is along the slope. So we should focus on forces that have components along the slope. Gravity does positive work because part of the gravitational force points downhill in the same direction as the motion. Friction does negative work because it points uphill opposite the motion. The normal force does no work because it is perpendicular to the displacement along the slope. The diagram shows the forces acting on the skier. The weight points straight downward. The normal force is perpendicular to the surface. Friction points up the slope because it opposes the skier's downhill motion. To find the net force along the slope, we need the component of weight parallel to the slope. That component is mg sine 25 degrees. Since this component points downhill, it is positive if we choose downhill as the positive direction. Friction points uphill, so it is negative. Therefore, the net force along the slope is mg sine 25 minus frictional force. This net force is what causes the skier's speed to increase as she moves downhill. Now let's solve this problem using the work energy theorem. The change in kinetic energy equals the total work done by all forces. For the skier, the forces doing work along the slope are gravity and friction. The work done by gravity's downhill component is mg sine theta times d. This is positive because it is in the direction of displacement. The work done by kinetic friction is negative Fk times d because friction points opposite the displacement. So the total work is mg sine theta d minus Fkd. The work energy theorem becomes 1/2 mv final squared minus 1/2 mv initial squared equals to mg sine theta d minus Fkd. Now we can solve this for v. Now we can multiply this equation by 2. So we get mv final square minus mv initial square equals 2 times mg sine theta minus fk times d. And then we can divide both sides by m. We get v final square minus v initial square equals 2 times g sine theta minus fk divided by m times d. And we can bring the initial velocity square to the right hand side of the equation. So we get final velocity square equals initial velocity square plus 2 times g sine theta minus fk divided by m times d. And now the square root of this will give us the final velocity. And now we can substitute the values. So we get 3.6 meters per second squared plus 2 times 9.8 meters per second square sine 25 degrees minus 71 newtons divided by 58 kilograms times 57 meters. And this is equals to 18.589, which is equals to 19 meters per second. Now we can solve the same problem using Newton's second law and kinematic equations as we did in previous example. The net force in x direction is equals to mass times acceleration in x direction. So the acceleration in x direction is equal to force in x direction divided by the mass, and this is equals to mg sine theta minus the friction divided by the mass. So we can substitute the values. 58 kilograms sine 25 degrees minus 71 newtons divided by 58 kilograms, and this is equals to 2.92 meters per second square. And now we can use the equation v final square equals v initial square plus 2 times acceleration times the displacement, and then we get v final is equals to square root of v initial square plus 2 times acceleration in x direction times displacement. We can substitute the values. 3.6 meters per second squared plus 2 times the acceleration is 2.92 meters per second square times 57 meters. And this is equals to 18.596 meters per second, which is equals to 19 meters per second. Both method gives 90 meters per second. The lesson here is that energy methods and force methods are consistent. Newton's second law describes how force produces acceleration. The work energy theorem describes how net work changes kinetic energy. When a problem gives forces and displacement but does not ask for time, the work energy theorem is often the most efficient method. So the main idea of this video is simple but powerful. Net work changes kinetic energy. Positive network increases speed. Negative network decreases speed. And zero network leaves the speed unchanged.